Right, let's make a start.
Based on feedback from the
I believe maybe a few more people will join in a moment, maybe start walking in soon. So we start by reminding.
I'll send that to you.
We start by reminding everyone about the code of conduct. Once again, if you have any concern, experience any misconduct or witness one, please reach out to the reference people. Respect everyone from their state of mental and social battery all the way to their level of comfort in contact. And don't hesitate to reach out if you have any concerns. And second, usual reminder to the virtual participants to please keep muted during the talks. And if you have questions, you can raise your hand at the end, or even preferably post the questions also on Slack so that it will be there for the record and maybe even easier to reply to. And without further ado, we will start the second session for TDS of this community workshop with the talk by Neven Caplar, who will tell us about scalable analysis across large data sets with LINCC Frameworks.
Thank you, Igor. So nice to be here. As mentioned, I'm a member of the LINCC Frameworks, so maybe you heard about it already yesterday. Our goal is to develop software and enable scientists to use the large-scale data. And this is what I will be talking about. We have multiple projects, but I will talk about the project which will be of most interest to this group of people, which is called LSDB, Large Survey Database. Okay, so it's a package which scientists can use, and the beauty of this package, the main idea behind is that we take the data, astronomical data, and it's stored in a hierarchical data storage where sky is split in hill peak tiles until each tile has roughly same number of objects and rows. And these tiles are stored within a directory tree. What does that actually mean? So if I have here our sky, we basically shard the data in this way where the areas on the sky where there's less objects, they are in single file. And then when you need more files in the denser areas, you basically can you go smaller and smaller so that each file has roughly the same size, but in the denser areas, just simply there's less area. And it's in this hierarchical structure where you basically know for each location where it is on the sky. What does this enable you? It enables you a couple of things. First of all, given the region of the sky, it's straightforward to find portions which cover the region. If you have a large survey and you're interested in only a small patch of the sky, you don't have to do SQL queries. You can just download this small part of the sky. Then you can also efficiently download a subset of columns because we store data in this format called Parquet. You can go within the files and load only the data that you are interested in. The other thing that this enables you, it enables very simple parallel processing. Let's say that you want to run a function over the whole ZTF. If you just separate the sky in equal chunks, what will happen is that some areas will have many more light curves. In this way, each file which gets sent to the processor takes the same amount of time, space in memory, and your processor should end also in roughly the same amount of time. Finally, maybe the most powerful feature is if you have two catalogs which are sharded in this particular way, you can very efficiently cross-match them because each region knows which files needs to look. You don't have to look for the whole database. You just need to pick that one catalog. And if you have many cores where each one can take these patches, the shards into memory, you can basically do whole sky on the speed that it would take you, that takes only one core. Okay, so I was talking a little bit about what are the powers of this format. I wanted to let you know what are we currently working on. So we are actually very actively working with NASA to provide data sets in this format. And this is with Space Telescope in Baltimore and IPAC in Pasadena. And we are implementing this on a Fornex, which is basically NASA science platform being developed to enable kind of like Rubin size platform, just on NASA. And we have been testing this with various data sets, some of these which I wrote here, basically for this group of people, probably ZTF and PanStars being the most powerful. And then we are developing within this LSDB that functionality where you have your own function that you can run your code with this package called DESC, which enables parallel computing. I wanted to a little bit mention what our plans for Rubin, where I imagine how Gaia would be overlapped with Rubin. Our goal is to provide Rubin data via Rubin Science Platform and independent data centers using the lessons which are now we are currently learning from serving ZTF and PanStars, enable bulk alert data access, and we will likely be providing thin tables of data releases. As you have noticed, basically in order to serve the data in this format, we have to basically duplicate the data and shard them. So we will likely not do that for the whole Rubin, just for the subset of the columns which will be of most interest to the community, but will also then be relatively light in order to enable multiple access points. But also, of course, we are actively looking for input, suggestions, and comments. The other thing which we are, if you're working in time domain in astronomy, we are developing this package, which will be integrated in LSDB, which is called Nested Pandas and Nested DESC. So basically, this is the Pythonic way to serve the data. For instance, if you work with ZTF in their releases, where basically you have the whole light curve as a single cell within your pandas data frame. And this enables you to grab the whole light curve at once and operate it. So for instance, just an example of the person who is using this for their analysis, it's Andreita Zinakis, who is a PhD student at the University of Washington. So here he's just showing what he's doing, where he's taking ZTF objects, ZTF sources, custom catalogs from Vizier. He's loading them all in LSDB, and then basically combining them and running his own functions. He's looking for objects which dip in ZTF. And the reviews are in, and the Nested DESC Pandas has been amazing. It has made analysis a lot more user-friendly, substantially faster. Now, from which default level, we can debate that. So if you want to use it, this is what you should do. We have conda packages, we have pip packages, we have a website, we have read the docs. If you have a small data set, you have your own 1,000 objects that you want to cross-match or operate on, you can just use this LSDB. If you have if you want to do PanStars, if you have to do a huge data set, then we have an additional package which is called HipScat, because this sharding we call HipScat, where you want to import these packages. Or you can use download data directly, which is already in this HipScat format on data LSDB.io. So this is the website where this data is available. So for instance, this is PanStars, it's 20 terabytes. You can download that if you want, but also you can just use on demand. And remember what I was saying to you, how the format is set up. If you just want some part of the sky or you want some columns, that's actually very efficient, that you don't have to load entire data set. You can be loading just that one file. And then we have, of course, a lot more documentation. Notice this is on AWS buckets, and this is a part of the open space initiative, which enables you to basically use that. This is a courtesy of Space Telescope. Okay, so conclusions. We want to enable scientists to use big data, and I was talking how this data is partitioned. If you want to use it, you just conda install it. There is lsdb.io. Join us on Slack, ask questions. If you're using time domain, we're working on this nested representation of the data, nested pandas, redox, and also linked time domain. I'm very happy if you could join and answer, of course, questions here.
For Neven.
So this is very nice, thank you. And so there's some cases where actually you want a just random distribution among all the shards. Because if you do spatial separation, eventually there will be one bottleneck depending on the class that you're looking for, let's say time series. So how do you consider this, and how did you?
Right, are you asking, like, I have 100 cores, and of course out of 99, one will hang because there are objects there.
Because the sharding was like, just for that particular question was beneficial.
Yes, I agree. You can't do all science cases at once, right? I think this is always a problem where you want to, there is a problem between having your code be super specialized for something, then it's super specialized. Then you want to be generalized code, but these generalized codes always have problems as you have probably described. I think what I have been describing is if you run large scale across the whole sky, but of course, if I run AGNs, my distribution of AGNs is actually, again, I'm not as efficient as if I sharded the data in the way which would have same density of AGNs, for instance. I agree completely, you know.
So do I detect that this is really very useful when somebody wants to run it on GPUs, when you can run a lot of parallel jobs at the same time? Not
necessarily on GPUs. That would be definitely a goal. We parallelize with DESC, which is basically, you know, it's parallelization for DESC. I think again, this is if I have a function and I want to do this first step of parallelization, I'm enabling you to run very easily on that. If you need to do something super fast and you're using, you know, GPU or then it gets more difficult. Having said that, I'm very interested in JAX that Charlotte mentioned, and we are using it successfully in that fashion.
Thanks.
Okay, if there are more questions, please post them on Slack. Let's thank Neven again. Our next speaker is Simran, and I believe the talk will be online. Simran, are you there? Can anyone please check if they're connected on Zoom, if Simran is present on Zoom?
I don't see him.
Okay, so we send a private message. In the meantime, I suggest moving on with the next talk, who is Maryam, who is also going to be remote. Maryam, are you there?
Yes, I'm here.
Would you be ready to present now?
Yes, can you see my slides?
Yes, we can. Can you go full screen?
Yes, 1 second. Okay, here you go. Okay.
Perfect. So Maryam is going to tell us about discovering explosive transients with Rubin+LSST, especially young stripped envelope core collapse supernovae.
Yes, hi everybody. I'm Maryam Modjaz. I'm faculty at University of Virginia. And sadly, because of various flight cancellations, I couldn't join you in person. I would like to make sure to acknowledge LSST Discovery Alliance for their childcare grant that would have enabled me even more to be present with you, but has also done it now. And I have a group of amazing people in our medal group whose projects I will also present today. So the title is a mouthful, right? Stripped envelope core collapse supernovae. So what are they? I will discuss them in a second, but nevertheless, they're very important. They're intrinsically as common as type 1As. And they tell us many interesting things about extreme physics because they're connected with gamma bursts, as well as with superluminous supernova and the last stages of massive star deaths. Since this is the last session today, I'll start with my take-home messages because I'm tired, I'm sure you're tired, jet lagged and so forth. So what are my take-home messages? I would like to convey a little bit of the kind of science area for some of the core collapse supernova people, which we've already heard earlier, that the field of young supernova and rapid transients is really emerging and rapidly developing. We've had a whole workshop on this in February this year in Bormio about, what are these things? What are their progenitors? What are their explosion mechanisms? So it's a very, very interesting new era of astrophysics. And we heard a little bit already about it from Azali, Manisha, and Samaya. So what are we doing in my group here? So we're trying to get ready by analyzing and curating current data sets. So far, even in this, non-1A field, there's been still a lot of single object papers and single object analysis, but not yet population analysis. And so that's what we're working on right now. So what I will do today is I will present the first population statistics of a sample of young stripped type 2Bs. 2Bs or not 2Bs, I will discuss them in a second. And more importantly, we find that the rise to this important shock cooling peak is around 1 magnitude a day. So that's going to be important for all the various filters that we will be designing for various brokers. And of course, we need high cadence. These things happen very quickly, rapidly, within a few days. And so we're part of the TVS Rapid Transients group and happy to work on metrics for that. And then we're also planning to get ready for LSST by designing a filter to detect these type 2Bs in current live stream data, such as ZTF Atlas and so forth. Okay, so this is my group. Some of them Fed is perhaps in the audience. So I've had a great pleasure to work with a number of people whose work I will present today. So briefly, every time we look at the sky in a different way, we find new things. And that has already happened just in the last 15 years. We found these weird objects called fast blue optical transients, or FBOTs, that are very fast, rise within a few days, and they're very luminous. And so that's the big question we have for many fields. What are the progenitors and what are the powering sources? They're very luminous. They cannot be driven by nickel 5060K. So what is it? And so just to remind us about the classification soup, alphabet soup, for perhaps some of the 1A people in the audience and others, other kinds of transients and stars. Usually we use spectra, right? We usually kind of Astro 101, we tell us we have spectra that we use. And what I will mention briefly is that they're actually time-dependent types. So all your beautiful classifiers and brokers that have these various subtypes, there is some caution because some of these objects, especially now that we have data of young objects, we see that they change, and that's very interesting and related to their physics. So what are stripped envelope supernova? Why they're important? So stripped supernova have been removed of the outer layers of hydrogen and helium, or both, and subtype Roland type 1Cs are connected with long duration gamma rays, superluminous supernovae, two superlatives, and even FBOTs, these fast blue optical transients. And some of them make jets. We don't know how. So I will discuss type 2Bs given the short amount of time we have today. 2Bs or not 2Bs. What are they? They are stripped supernova that have a little bit of the hydrogen intact as well as the helium layer. And so usually when you think of a supernova, you think of just a rise and a fall. But type 2B supernova, when caught early enough, have two peaks. So the first one is driven by what's called shock cooling emission. And the second one that we kind of know and love for many, hundreds of years, is the nickel powered one. And why is the first one important? Well, it tells us uniquely about the radius of progenitor and the CSM of the progenitor. And especially the radius of the progenitor is crucial. There are no other ways except pre-explosion HST images that only go out to 20 megaparsecs to get the radius of the progenitor, really do stellar forensics, understand the progenitor before it explodes. So the work I'll present today on 2Bs is going to be based on my grad student Adrian Crawford's work and their amazing graphics that you will see, and the hat, which seems like stellar detectives always have, and the magnifying glass. Yeah, but before we talk about the population of type 2Bs, I want to give a shout out to our postdoc in our group, Craig Pellegrino, who had a very recent example of a type 2B, where the first peak was 1 day after discovery. So less than 2 days after explosion. So these things are very fast. So to catch the very important first peak, you have to, be catching them in a very high cadence. So this was an interesting object. We can talk about it. The paper is out, but for the purpose of kind of this talk and for LSST looking ahead, I do want to make sure to acknowledge the rise time, which is, you know, less than 2 days after explosion. Okay. So what did we do with a data set? So we used what Adrian calls the lightning model. And why is that? Well, it looks like a lightning bolt. And we wanted to quantify how fast is fast when we talk about fast transients. And why is that? Well, because broker filters, or the filters we want to design for brokers, easily trigger on the rise or certain kind of change in magnitude, right? So that's what people also use in the literature. They assume some assumption, you know, make some assumption about the rise. But here we want to actually measure the rise based on a sample of type 2Bs. And so we fit this lightning bolt model with these various parameters, the 7 parameters, to really focus on the first peak. Since we care about early detection, we didn't look at detail at the second peak, except for this rise to the second peak. No, can you see my mouse? Yeah. So what we do is, what Adrian mostly did was use MCMC to fit our gold sample of type 2B. So it turns out there's, you know, different completeness levels for different type 2B. Sometimes they only have the decline after the first peak. So we use this gold sample where you can see the rise, where you can get M1, which is the rise, the slope to the first peak. And we use force photometry data from ZTF, Atlas, and Assassin. So thank you, everybody who worked on making these data available. They were very, very valuable. So what did we find? So we had a gold sample, and we, of these objects, 13 of them, there's a small sample because we wanted to focus on alert stream data as we have them now. And we have R band and of course I band data, for which we did. And then we put together the mean best fits for the sample. And so what did we find? One of the highlights is what is fast for cooling shock emission for 2Bs. We find that it's around 1 magnitude a day, which is 10 times faster than the rise to the nickel powered peak, the main one that, as I said, we know and love for kind of hundreds of years. This one is 1 magnitude a day. And we have the number in G band and R band, and hope to answer Azali's question in TVS1, which was, what is the color evolution of young supernova, in particular type 2Bs? So what's the next work? And I'm almost done. We're going to expand the data set, 13 objects, while, you know, worked very hard on and found and, you know, loved is not a big number. So we will be using Gaussian processes to create data-driven synthetic light curves, because even though there are models, they're very model dependent. If you look at the literature, you have differences of factor of 10, for example, in radii that they then would infer. So we're going to do a data-driven set of synthetic light curves. We're going to refit this lightning model with, do some more perform feature engineering. And with all of this together, we hope to develop an alert filter with perhaps Antares to create then an ML classifier to find these kind of important nuggets, these young 2Bs. Of course, a lot of work has already been done on what's called Presto Color by Fed, Bianco, and others to identify a very interesting object. So this is an important topic that has been already discussed, and we're happy to contribute using now data on 2Bs specifically. And then my last slide here is to show you that in this kind of era of fast evolving transients, there are many kinds of fast evolving transients, and you need to really have spectra, which you know, we won't have for many, to figure out what they are. So there's this Ho et al. Sample that has been discussed before, and 3/4 of these type 1 CNs, which is this new type of supernova, very small sample, but astrophysically very interesting. They would be called fast evolving transients if we didn't have spectra, which is these kind of set of spectra early, you know, very early on that Craig Pellegrino worked on. So if you're interested in the physics, I suggest to look at the paper. Okay, so conclusions here are, we are very excited about young stripped supernova in our group, and we want to prepare for LSST to find them with other perhaps synergetic projects that I've heard today. So we have many ways we can do that. The one I discussed today is to look at young stripped type 2Bs, again, a mouthful, but very important subclass of supernovae. And we hope to detect them in kind of a rehearsal run in current ZTF Atlas surveys to take out all the kinks before we work with LSST. But of course, it's important to think about the cadence, and so I look forward to the discussion tomorrow or Thursday, and also to work with the TVS Rapid Transit group to think about what kind of cadence would be needed to do the science, even if it's a small percentage. Even if it's 1% or less, I think it'll be very interesting. Anyhow, if you we have also other interests in my group to help improve photometric classifiers, so talk to me in my group if you're interested. We have spectroscopic templates, so spectroscopy that we won't have in the future, but have now to do K corrections, so really redshift them as a function of redshift, using the fact that these have lines, right? These are objects. These are not black bodies. A lot of people in the supernova field talk about black bodies. Supernova, by definition, are not black bodies. Perhaps at early times, cooling up envelope emission, but of course, you see the lines later on. So co-corrections are important. And we're also working on a UV data catalog based on Swift to put together UV data that will be necessary for redshifting them into the optical, which then LSST will see for high redshift objects. And see, these are all kinds of transients. Okay, thanks. I'll stop here.
Questions for Maryam?
Yes.
Manisha.
Just out of curiosity, for the 1CN, is there any chart like with broad line feature or anything where you have the interaction as well?
So the 1CNs, so these have narrow lines, but they're P Cygni, right? So they're not just interaction driven, but there's also P Cygni, which tells us about CSM before the explosion. So, and what is broad? I mean, for me, these are not broad. I work also on broadline type 1Cs connected with GRBs that have 30,000 kilometers a second. But they're also, so they're in that sense, they're quite narrow. But they are P Cygni, it's, meaning it's optically thin, what we're looking at.
Okay, so we don't know if Simran will join later. They have not replied to my message yet. I suggest we keep on time just in case. We can ask Maryam more questions on Slack, or perhaps organize a chat if anyone needs to. Thank you, Maryam, again.
Okay, thanks.
Next talk is by Narayan Khadka. Is that correct? Yeah. Yes, here's this one. Okay, and let me share the screen 1 second. And Narayan will tell us all about SLSim.
Yeah, SLSim.
SLSim, strong lensing simulation pipeline.
Yeah. Hi, everyone. My name is Narayan Khadka. I'm a postdoc at Stony Brook University and also a pipeline scientist in DESC. So I am working on strong lensing simulation pipeline since last year. And I'm going to talk about that today. So SLSim is a Python-based software package that can simulate different kind of lens population. So the question is why we need simulated lens population. So we need simulated lens population for validating lens finding algorithms, and also to validate light curve extraction algorithms, and also to validate lens modeling algorithms. And for all these purposes, SLSim can provide the training set and testing sets. So here is the structure of the SLSim. So in the diagram, you can see how different components of the SLSim are connected with each other. So SLSim is very well tested and well documented code. So you can see the current code coverage of this software is 98%. And we have provided documentation for almost all the functions or class that we have in the code. And this project is under the Strong Lensing Science Collaboration and Dark Energy Science Collaboration. So currently we have 18 contributors so far in SLSim, and this number will increase in future. So let's talk about what are the main functionalities of SLSim. So as I said, it can simulate lens population. The lens can be static or variable, depending on user's requirement. And then it injects simulated lenses to the cutouts from the DP0 DP0 data. So, and then finally it returns a catalog of realistic lens images. And also this can be easily adapted to the Rubin simulation too. So to generate lens population, two fundamental ingredients in SLSim are lens catalog, source catalog and deflector catalog. And for the source catalog and deflector catalog, galaxies catalog can be generated by using SLSim. Within the SLSim, there are different pipelines, and we can actually call these pipelines to generate galaxy catalogs or supernovae sample or quasar sample. And also, one can always use pre-computed source catalog or deflector catalog in SLSim. So in that sense, it's very flexible, it's very modular. So here are some distribution of galaxies generated by using SLSim. One can use SLSim to generate these galaxy distributions. And the first kind of lens population that we can simulate is galaxy-galaxy lens. So here is a corner plot showing population of galaxy-galaxy lenses within a 1 degree square sky area. And once we have a lens population, we can simulate images of those lens population by using image simulation module, which is inside the SLSim. And here is an example. So at the top, you can see sample of simulated lenses by using SLSim before injection to the DP0. And at the bottom, you can see sample of injected lenses, the galaxy lenses after injection to the DP0 data. So the second kind of lens that we can generate, we can simulate by using SLSim is lens supernovae population. So this corner plot shows population of lens supernovae, and this is implemented by Carly Mystic, who is a student at Stony Brook University. Here also, once you have a lens supernovae population, you can simulate images, and you can simulate time series images of the lens supernovae, and also at the same time you can create time series cutouts by using DP0 data, the single exposure images from the DP0 data, and then you can inject time series lens supernovae image to the time series DP0 data. And here is an example of that. And then the third kind of lens population that we can simulate by using SLSim is quasar lens, lensed quasar population. So this is again a corner plot showing population of lensed quasar within a 100 degree square sky area, and this is implemented by American Sonmes, who is undergraduate student at Stony Brook University. And here also you can simulate images once you have a full population of a lensed quasar. So to simulate time series images of a lensed quasar, you need a quasar variability model, and we have a quasar variability model in SLSim. This is implemented by Henry-Best. So here is an example of quasar light curve generated by using quasar variability model that we have in SLSim. So once you have a light curve of quasar, then you can simulate time series image here. And similarly, as I mentioned in Supernova case, you can create time series cutouts from the DP0 data, and then you can inject those time series lensed quasar images to the DP0 time series cutouts. So the fourth kind of lens that we can simulate by using SLSim is cluster lens. And this is implemented by Philippe Worsley. For now, we can only simulate individual cluster lenses in SLSim, meaning we cannot simulate population of cluster lenses. Just you can simulate a single cluster lens if you want. So, and the next step for this is the next step is we want to have a code that can actually generate population of cluster lenses, and we are working on that. And here you can see two examples of cluster lenses that we simulated using SLSim. So another important task that we did with SLSim is SLSim validation with DESC resources. So we just wanted to see how good or how well we perform with the image simulation in SLSim. So for that, we picked up one galaxy from the DP0 and then simulated image of that galaxy by using SLSim and compared that image with the DP0 image of that galaxy. And you can see in the image, they are pretty much same. So, and another verification that we did is validation of galaxy distribution. For this, we compared, so SLSim, so for this we compared luminosity function of, for this we compare luminosity function of galaxy population simulated by using SLSim and the luminosity function of DC2 galaxies and also deep sky galaxies. So in different redshift bins, and you can see these luminosity functions are matching very well with each other. So that verifies we are doing well with the galaxy simulation too. So here are ongoing, so the ongoing developments, we have more than 10 ongoing tasks, and also there are more than 5 so tasks under to-do list. So if you want to see all these lists, you can visit SLSim progress tracker in GitHub. And if you want to contribute, so I'm very happy to discuss your idea. And if you are also interested in so if you are interested in any project that is in to-do list, so yeah, feel free to reach out to me. We can discuss about that too. So future plans. So we are planning to use the simulated data, simulated lenses from SLSim to a static lens finding challenge that is under progress. And also we want to use lens transient. We want to use so lens supernovae or lens quasar data for lens transient sort challenge. And also we want to test performance of the DIA pipeline with resolved and unresolved lens transient images simulated by using SLSim. And also, so we want to use this data to validate or we want to use this data to in pixel to light curve and light curve to time delay challenge. So that's another future plan. And finally, we want to do in cosmological inference, which includes lens search, finding, and analysis to get accurate cosmological constraints. So the conclusion here, SLSim has capability to generate realistic lens sample or lens, realistic strong lenses by combining simulated lenses with the DP0 data, and we can use this data to validate lens finding algorithms and light curve extraction and time delay extraction algorithms and lens modeling algorithms, and also for many other purposes. Yeah, thank you.
Perhaps we can have one question live for Narayan from either the room or from Zoom.
maybe you already covered it, but it's a nice talk, by the way. Thank you. Yeah. Is there any way that one can also say custom design some simulation through through that code? Say you could give it certain inputs rather than only just draw from LSST.
So you mean like the cutouts? I don't know.
I mean that there could be some parameter set, for example, and you could give custom inputs of those parameters in order to simulate. You know.
Yeah, I mean, you can put many cuts in to customize like the lens population sample. You can actually put many cuts there, like the magnitude cuts as your requirement, and also magnification cut, and also like other like the arc magnitude of the arc. So these kind of cuts can be applied there, and you can customize the sample.
Oh, okay,
So-
but not the mass of the lens.
No.
Okay, all right, that's good. Thank you.
Right, let's thank Narayan again. And our next speaker is Brenda Frye here in the room.
There you go.
It was very nice slide anyway. And will tell us about measuring H0 with JWST GTO Pros program.
Okay, hello, yeah. So I suppose the objective of this talk really was to hope to get some interest. Sure, we already have the interest, but even more interest, not only in detecting supernovas with Rubin+LSST, but also lens supernovas, lens supernovas behind, lens supernovas lens by clusters. So that's the point of this talk. And what's a bit unusual in my research group at University of Arizona is I work with a lot of early career scientists. These are the main people I worked with in the nice data and results I'm showing today, and everyone listed in dark orange are students, undergraduates, graduates, and postdocs. It's a very large group, and we meet daily actually to keep everyone up to speed. Okay, so here we go. We detected a supernova behind this cluster. So basically observations of this cluster, which I call G165, were acquired with the James Webb Space Telescope, guaranteed time observations in a program we call PEARLS. This cluster was selected because it has a high star formation rate of background sources summed up over the single field of view near count. So it's a bit of an unknown name, but we wanted to select based on those clusters that might have a high incidence of supernova. So we detected a supernova behind the cluster, and yay, and well, which type? Well, even if it would be a core collapse supernova, then because it's behind the cluster, it's higher redshift, so that would be enough to increase our understanding of high redshift core collapse supernova. But it was a type 1a supernova, and that gives us something extra special because it also makes it a standard candle. It's a little bit more unusual to detect higher redshift type 1a supernova. And that also would have been a reasonable result and enough to be pretty happy. But that type 1a supernova is seen in 3 different locations at the same time. Detected in image A, image B, and image C. And it has a host galaxy, which we call ARC 2A, 2B, and 2C. I went ahead and put up a cartoon on the right-hand side to make it easier to see some of the patterns where we show the supernova and its host galaxy relative to each other. The image parities are flipping between the images as they cross the critical curve each time as expected of lensing theory. So that's how right away we said, oh, right, we don't have 3 different supernovae detected behind this cluster. We have a triply imaged single supernova. It tells right away, here's the actual data. Seeing is believing. And you might also notice that they don't look exactly the same, do they, right? You think the supernova arrived first to image A, second to image B, C, sorry, and third to image B. and image B is the brightest. We intercepted image B very close to peak brightness of the supernova. Why do they have different brightnesses? Well, because of course we intercept them during different times of their explosion. Okay, and we can take a stopwatch and measure the time difference in the arrivals of the supernova to each of the images. Okay, and with those time differences, a lens model, and the lens and source distances, we can measure H0 by the method of time delay cosmography. So that was the plan. And just a triply imaged core collapse supernova would have been enough to measure H0 by this method of time delay cosmography, as I just described, and that would be nice. But we were able to, detect a triply imaged type 1a supernova. So we get the benefit also of the absolute magnifications. And we'll see that it helps us to obtain a more accurate value for H0 and also to weight the values. Okay, so what you're looking at here is one epoch of JWST observations in the G165 galaxy cluster. Here's again where we see supernovae and appear 2A, 2B, and 2C. If we had just this one image, then we'd already get 3 points on the light curve, right? Because you see them 3 different times in one image. And that would be nice. We would just, get a borderline, get fit to a light curve and measure the time delay. But we were fortunate instead to get 3 observing epochs. So we get 9 points on the light curve, little more reasonable number with which to fit a light curve. We're able to fit separate light curves for epoch 1, epoch 2, and epoch 3, and measure that time delay. Now, in a kind of more novel and unusual turn of events, we were also lucky enough to obtain spectroscopy of all 3 images of the supernova as well. And we measured, one could call it a spectroscopic time delay, right? Because we know that the spectrum of a type 1a evolves over time. And built up a lot of nice data over that. So we're able to measure the supernova phase, and from that, obtain this very special spectroscopic time delay. Okay, so with those time delays and absolute magnifications, 3 of them, with the 3 different images, we obtained 5 observables moving forward. So we have what? We have time delays now, we have lens and source distances. Oops, sorry. The supernova is a redshift of 1.783, and we just need the lens model. Last thing. Okay, so we reached out to the whole lensing community, tried to commission as many different families and approaches of lens models as possible. I didn't know there were 7 or more lens models, but we got them. We blinded them all from each other and from the photometry and from the spectroscopy. And I worked really hard at policing that for several weeks. And then we gave them a uniform set of lensing evidence. We gave them identical cluster member sets, fields of view, and fiducial cosmology. So H0. And then they returned to us their values for the 2 time delays and the 3 absolute magnifications. We then rescaled their value for H0 until their predicted values matched the observed ones. And we ended up getting H0. Now this looks like a lot of, oops, sorry, I don't want to release, try to use the laser pointer. This is our result. You can see H0's up here. Don't worry about all this mess. The main thing is that when we try to measure H0 based on only 2 observables, time delays, we get interesting, nice value here. And we see that each one of these colored curves is a different lens model contribution. With many contributions, we can't really grade them, tell which one is better than another very well because there are some degeneracies. Then when we're finally able to include also the photometric, all the photometric information, including absolute magnifications, we see that we're able to start discriminating between models. We get a very similar value, but we see that the model contribution weights change. And then finally, when we included both the spectroscopic measurement of the time delay and the photometric measurement of the time delay, we do see, interestingly, for this particular case, not for all cases, but for this case, one particular model does seem to receive the highest grade, the highest weight, and that is our best value for H0. Why does anyone really care? Well, haven't we measured H0 before? Yes, many, many times. Some people in this room have done beautiful jobs, and you know, our value is, you know, has pretty high uncertainties at this point. But what you can notice, what you might have known over the past decade, is that the measurements of H0 seen at, you know, late cosmic times is different from the value for H0 measured at early times. I want to understand this difference, this tension between the two values. So having additional independent methods for measuring H0, like this one, you know, won't in and of itself solve the Hubble tension, but it can elucidate it. And that's all. I just wanted to put up this final picture here of the cluster and all the different arcs in supernova, and say that, you know, the future here looks really bright. Okay, Rubin Observatory opens up the discovery space for this type of work, right? This is only the second time this measurement has been made, and the first time ever using a type 1a supernova. So if there's any interest to talk further, I'd love to plan more. For looking forward to Rubin. Thank you.
So do you need to deal with massive degeneracy here?
No, well, so first of all, cluster lenses are a little bit easier to work with than galaxy lenses, in that Meshic degeneracy is always partially broken once you have two or more image systems at different edges. So we already know we partially break that degeneracy. We also work with larger scales, so it's, you know, a little bit easier for us. Do we completely 100% break all possible Meshic degeneracy? No. So if you read the paper led by my student here, the 6th one, Pascal et al. 2024, you'll get to read words and words and words about it. Thanks. Yeah.
One more
This is a
question.
very quick question. What's the redshift of the cluster?
0.35.
Okay.
And as usual, if I have a question, please post them on Slack. Let's thank Brenda again. Yeah. And the next talk would be by Anupreeta. Yeah, they couldn't find here. So stop sharing. And some good news, Simran managed to come online and will give the talk at the end of the session. But if everyone keeps on time, we should be able to finish by 5:30. Okay. So Anupreeta will tell us about uncertainties in time delay cosmology with lens transients. Take it away.
All right, thanks very much. Hi, everyone. I'm Anupreeta More, and I'm going to talk about what are the uncertainties one has to deal with, how realistic these uncertainties are if you want to look into the time delay, cosmology with time delays, or generally different science that would want to do with time delays using lens transients. Okay, I just here.
Of course.
Right, so just very briefly, we've heard about the tension in the H0 in the last few years between early universe probes and late universe probes, and we would like to have more and more independent methods that can look into constraining the H0, especially to get better hold on the systematics from different methods. So for strong, we can do H0 measurements using strong lensing systems. So in strong lensing, we can see multiple images of a distant background source. If the source is a variable source or a transient source, then we can measure the time delays between the multiple images. These time delays are
That's gonna
No,
control the.
So I'm going to make use of this. So the time delays between the different images, they depend on the angular diameter distance ratios, the lens redshifts, and these two main parameters here. One of them depends on the differences in the geometric paths that are traversed by the different light rays, and also the different gravitational potential that is experienced by the different set of light rays from corresponding to different images. And so if you measure these time delays and get a hold on the lens potential, plus if you know the lens redshift, then you can constrain the H0 through this distance ratio factor. And so this strong lensing provides a completely independent and one-step measurement of H0. And so in the last few years, in the field of strong lensing, we have had constraints on these cosmological parameters, specifically H0, through these various detailed studies done using strongly lensed quasars via the Cosmograil, Holy Cow, and TD Cosmo collaborations. And more recently, as you also heard from Brenda, there have been studies of lens supernovae, which have also helped in constraining H0. But I'm going to talk slightly in a different way. For example, if we are looking at lens gravitational waves and looking at their electromagnetic counterparts, which are kilonovae, then what kind of science we can do, or what kind of improvement these kind of lensed gravitational wave sources plus their electromagnetic counterparts can bring in. So there was a study by Liao et al. A few years ago, in which they pointed out that if you have lens gravitational waves along with their electromagnetic counterparts identified, then just with a handful of these lens systems, you can get much tighter constraints on the cosmological parameters compared to the lensed quasars. And the thing that they pointed out here is that the sort of uncertainties that one will get on the time delays are going to be basically negligible if you're looking at lens gravitational waves. And another improvement comes from the uncertainty in the lens potential here, which is going to be far better compared to the lensed quasars. And so we have tried to look into this particular aspect as to how realistic these uncertainties that are quoted here, how realistic they can be. So we are trying to do this by doing some analysis with mock lenses. So the idea is to generate mock HST-like lens systems in different configurations and different types of images at galaxy scales. So either doubly image or quadruply image. And the idea would be to compare the true lens potential for a pair of images compared to what you find from fitting a lens mass model to it. And so we basically quantify this delta del psi that was quoted in the Liao et al. Paper. We do this for different kinds of lens system. And so here are some preliminary results. So the plots show for different image pair combinations for quadruply lens systems and for doubly lens systems, what are the delta del psi one can get. And in this particular case, we are fitting a lens mass model which has the same density profile as the mock lens that was generated. So that is specifically that is power law plus shear in this case. And in such a scenario, where the noise and the PSF uncertainties are also fully known, we get much better uncertainties that and much smaller than uncertainties that are quoted in Liao et al. Paper. And so in the next few steps that we're going to perform, we're going to relax some of these assumptions. We're going to test lens mass models which are completely different from what is there in the mock data, and also introduce realistic uncertainties in the noise and the PSF models, and see how these uncertainties are going to become worse and worse. Another study that we did from the perspective of cosmology and studies of progenitors of these lensed gravitational wave sources and the corresponding EM counterparts is to try and understand what sort of time delays we'll expect to find, how these time delays and their uncertainties change as a function of the lens redshift and the source redshift. So here in this plot, we show on the plot on the left hand side, we show how the time delays change as a function of lens redshift and the source redshift. So we find that the time delays are much higher if your redshifts are much higher, but we also look at the relative uncertainties in these time delays, which seem to be more or less constant in the space that we have shown here. And we've also tried to compute the fraction of lenses which will have time delays of so like minimum time delay in a large sample of lenses. This is to be able to find lens systems early on so that we can trigger appropriate follow-up in the electromagnetic or even in the gravitational wave community, so that we can catch these transients very early on. So like you heard from Maryam, how important it is to be able to catch the transient at its rising phase. So if we able to identify a lens transient candidate and quickly model the system, we can make predictions for the time delays, and we can then make sure that the telescopes are following those particular systems very early on, so that we can catch them in the rising phase. And so what we have computed here are what are the minimum time delays in a sample of lens systems, such that the time delays can be greater than 1 hour or greater than 1 day. And this is computed for 2 types of lens gravitational wave sources, which can have electromagnetic counterparts. And the numbers are also shown for increasing detector sensitivities in the gravitational wave detectors. And what we find is that for the next generation, a large fraction of the systems will have time delays greater than 1 day. And we have also explored what are the kind of uncertainties we will have on the time delays if the time delays are of the order of several hours. And what we find is that if our astrometric uncertainties are at the level of HST-like images, in these cases, we can make predictions up to a few hours or like few tens of hours ahead of time. Of course, we would like to do this with more realistic scenarios, which means we would like to work with ground-based resolution or ground-based astrometric uncertainties. So more recently, we have tried to now do this analysis with lens systems, which are common to both HST kind of data quality versus ground-based data quality. So these are the systems which are identified from the HSC survey. And so here is some preliminary results where we have modeled these systems, both which are common to both, HST and HSC, and we're trying to compare how the time delay measurements or the time delay predictions from our analysis, how they change when we go from space-based kind of resolution to ground-based kind of resolution. And what we find here from our preliminary analysis that the time delays that we can predict from ground-based data, there can be differences of the order of like 50% or so. So we're going to do this analysis with more and more systems. This particular result is for real lens systems, but we are also going to do this analysis with mock lenses so that we have better understanding of what are the true time delays. Yeah, so we're going to do this further. So I would just like to end at this point here and say that if you want to do with cosmology or early warning kind of science with lens transients, it is very important that we understand what are the uncertainties in the time delay predictions and generally the different uncertainties involved in the modeling of the lens systems. And we are looking into some of these, and I would just like to say stay tuned for some results that will come out of our group in the next few months. Thanks.
Any question for Anupreeta? Could you please come a bit closer to this part of the room for people on Zoom to listen?
Thanks for the talk. So just a quick question about the redshift distribution you expect for the gravitational wave source, lens gravitational wave sources, because these look quite high from the ones you simulated, but to be detected by the ongoing gravitational wave observatory is, will we really reach up to like redshift 1.4 or something?
Yeah, so the thing is that if you're going to specifically talk about lens gravitational wave sources which have EM counterparts, they will come from slightly lower redshifts. But the thing is that it's also true that the ones which we'll actually detect, they will likely be very highly magnified, and so they might actually come from slightly higher redshifts than is possible from the typical horizon for the gravitational detectors. So I would say some redshift something like 0.2 to 0.4 is not something very unrealistic, and the sources coming from like redshift 1 and above is completely possible, and you will be able to find a more relevant plot in Graham Smith's paper, where you can see where is the detectable population coming from.
Thank you.
Yeah.
Any more question? Greg, anything from Slack?
I don't see anything on Slack.
Then let's thank Anupreeta again. The next talk will be by Ryan. Ryan, are you connected?
Yeah, I'm here.
Hey, good to see you.
Hi.
Can I share your screen?
Yeah.
Or do you want me to share from here and I move?
I can share it. It's all good.
Sweet. So Ryan will tell us all about inferring CSM properties for type 1a supernova using a magnitude limited ZTF sample. Take it away.
Thanks. So yeah, my name's Ryan Hines. I'm a third-year PhD student from Liverpool John Moores in the UK, so it's a bit late for me, but I'd like to thank the organisers for allowing me to talk. So yeah, I'm going to talk about using type 2 supernovae and a magnitude limited sample from ZTF to infer progenitor properties. So we're interested in type 2s and type 2s and CSM just because we're interested in their progenitors. So it's been known for a while now that type 2 supernovae have a red supergiant progenitor, and so we're interested in the end of life mass loss because it's not well constrained. Is there a period of enhanced mass loss? Because what we see from single supernova studies is that the mass loss inferred from transient or from the spectroscopy is higher than the mass loss of red supergiants we observe, and so we're trying to understand the extent to which the CSM is there and how it got there and the rate at which it gets there, and so as that constrains the period of this enhanced mass loss. And so as I suggested, or as I said previously, we know that there's CSM around type 2 supernovae from transient emission lines. So this is from shock ionization of the CSM, so that's where the shock breakout ionizes the CSM. And so these transient emission lines appear and disappear within a few days, so that tells us that it has to be a confined and dense CSM. And so we can infer this quite readily now from spectroscopy, but you have to get on early enough and you have to have a high enough resolution to really resolve these features. And so what we're interested in is using photometry with the upcoming surveys like ZTF and Rubin now. Photometry is going to be the main resource we have, and so we're interested in gleaning as much information from the redshift as we can, or sorry, from the photometry as we can. So I'm working with ZTF at the moment, particularly the Bright Transient survey. So I won't introduce ZTF, but for those of you not familiar with the Bright Transient survey, it's a public survey along using the public ZTF survey. It's a magnitude limited survey aiming to spectroscopically classify all extragalactic transients that peak above or below 18.5 magnitudes. And so to date, it's the largest supernova catalogue and most complete. So up to 18.5 magnitudes, it's around 95% complete, and we've classified around over 9,000 supernovae. And so this is a very complete sample with high cadence light curves, and so we want to really be able to glean as much information as we can from these. So what I've been doing is using Gaussian process regression to model these light curves, interpolate them, and try to extract as much information as I can. So I started with a 1D Gaussian process, which approximates magnitude or flux as a function of time. And I've moved on to using the 2D Gaussian process. So I incorporate the effective wavelength. And so I'm able to use all the photometry as one single Gaussian process. And so that enables me to better constrain behavior in each band depending on the behavior in successive bands or nearby bands. So you can see the effect it has on G band if you look at the 1D compared to the 2D. I mean, on I band, which is the blue curve, you can see it really constrains the rise. And so we're able to get a lot more measurements out, or a lot more constrained measurements, especially color evolution and the rise time particularly. And so using this force photometry and the Gaussian processing pipeline I've developed, I have applied this to all of the transients in the BTS. So as of writing this, that was 8,000, but it's closer to 9,000 now. And the goal is to make these really nice light curves, and so we can extract as much information as we can. So these are the type of light curves, some of the better sampled light curves that we have in the Bright Transient survey. But I'm able to measure as many empirical relation or empirical parameters as we can, basically. So things like the peak magnitude, the rise times, the peak colors, partial durations, fade times, and even get into some optical GRI energies or pseudo-bolometric luminosities by integrating under the light curves. So we're focusing on the rise time specifically, as I alluded to. The CSM is affects the rise time. So the rise time is sensitive to both the CSM and the progenitor radius. And so there's been studies showing how a model that includes CSM fits better to the rise and the absolute magnitude of the peak than models without CSM. And so we're interested in trying to quantify the level of CSM in a statistical manner. And so we're able to do this with the Bright Transient survey. So to do this, we've defined the G band rise time as the time from 75 to 25 or 25 to 75% of the max flux. So that really tries to tries to measure the time which we think the CSM is going to be most important, because as we know, it gets swept up as the ejector moves through the CSM, and so we're trying to use this rise time to as a signifier of CSM, as we think a dense CSM will brighten the luminosity, so make it more luminous at peak and decrease the rise time. And so with the magnitude limited survey, which is highly complete, and these empirical relations, or these empirical parameters, we can make these volume corrected distributions, so volume corrected by Vmax method, and create these nice probability densities essentially. And so this is a rise time, the same rise time as I described previously, rise time kernel density estimate for type 2s, and we find the median rise time is around 3 days, which is very fast, and it's hard to explain that without some sort of CSM and interaction between the CSM and the shock breakout. And so we can create these nice luminosity rise distributions where we can see the kind of phase space that type 2s occupy. So type 2s are in green here, 2Bs are in blue, and they occupy like the lower half of this plot. You have 2Ns in orange, they're more luminous and slightly longer. And then you have superluminous in pink up here, which is what we expect. I've also added on some model light curves that included CSM. So a few slides ago, I talked about light curves that required CSM to be modeled accurately. So I've included those, measured the rise time and the peak absolute magnitude. And if you put on 2023 AUXF, it lies around this area of phase space. So it's typical, but it's towards the upper echelon. So that's quite nice to see. So with those model light curves that required CSM, I was able to fit empirical relations between the CSM properties, so the mass and the radius, to the rise time and peak absolute magnitude. So we find quite strong correlations between these parameters, and so we fit a relationship to them. and we find this nice form of a relationship with minimal scatter. The idea is that we'll be able to apply these relations to the empirical parameters we've measured from all of our light curves and create nice, again, volume corrected distributions. So we can do this with CSM mass, and we find a median CSM mass for these type 2s that once we apply our quality cuts is around 300 type 2 supernovae. And we find a median CSM mass of 0.086 solar mass. But the key quantity here is the proportion of events that have, or we estimate to have above 0.1 solar masses worth of material. And so that's quite a large proportion of the population, and it's volume corrected. So we're commenting on the population as a whole within this magnitude range, which is it's owing to the idea of this enhanced mass loss period. And so if you take a stellar average wind velocity around 10 kilometers per second, that's a mass loss rate of around 10 to the minus 3 solar masses per year. So that's agreeing with these single supernova studies. And so you can do this with the radial extent as well. And so you find that it's for a large majority of supernova that the CSM is quite confined. This is on a smaller sample, so we're a smaller sample of models. So we're upgrading the models to incorporate a lot larger, less coarse parameter grid of masses and CSMs radii. But that's the basic idea. And so we're just writing up the paper now, and hope to have it out in the next month or so. So thanks for listening. I'm happy to take any questions. I'll just leave my my conclusions on here.
Francisco has a question for Ryan.
So thank you for the talk, very, very nice. So the relations, some of the relations you're finding, they sound to me like, I don't know if you've seen the paper by Silva et al., Javier Silva.
No.
So basically, using type 1As, type 2 supernova, sorry, we were able to derive distance very accurately. And we believe maybe related to the early part. So, and the fact that there are so many correlations that you're finding at early times, I wonder if this could be used somehow to use it as a distance determination method.
Okay. I'd be quite interested to hear about that a bit more. We can talk over Slack. That'd be quite interesting.
Okay.
Thanks.
Thank you.
Ryan, a quick question from me. What do you see the potential of Rubin for this science case, or the challenges?
So I think the challenge, just to get that out of the way first, I think would be the cadence, because we're really trying to probe the early time, and that evolves quite rapidly. But the benefits kind of are the much improved wavelength coverage. So you're really able to find the color and how it evolves over time. And something like this Gaussian processing, it can make use of the various filters. So we're limited to 3 with ZTF, and they're it's a limited range, but with Rubin, it's going to massively improve. And so I think it's the amount of information you can glean kind of makes up for the cadence, because the filters will help influence each other. And so I'm quite excited for both the amount of supernova we find, but also the photometry that will come as part of that. And the deeper we go, we'll be able to find more supernova and follow them from longer, which will be nice as well.
Great, thank you very much.
Thanks.
Last but not least, Simran managed to connect, I believe. Simran, are you on the line?
Yes, can you guys hear me?
Yes, we can hear you well. Would you like to share your slides?
Sure, thank you.
Okay, so Simran will tell us about the quantification of the impact of standard Sirens for DESC cosmology results using LSST.
Hello, everyone. My name is Simran. I am a PhD student, second year right now at University of Michigan. I'm working with Professor Marcelis Flores Santos and others on this project that we have within DESC primarily, but it is based on the forecast for the Hubble constant measurements, how precise we can get with LSST in future. Starting with some basics on the Hubble tension. This is one of the biggest questions in cosmology today, how we want to resolve the tension that we have from the measurements that we get from the other probes, like the type 1a supernovae using local distance ladder technique and the cosmic microwave background results. So with the establishment of LIGO-Virgo gravitational wave experiments, we were able to find a new way of distance measurement, which in turn helped us a lot in measuring Hubble constant. In gravitational waves, we have these three types of mergers between two neutron stars, a neutron star black holes, and two black holes. In case of these neutron stars, whenever a neutron star is involved, we use something called standard Siren techniques that help us measure Hubble constant. While if we have two black holes, we use dark Siren techniques. This particular project focuses on the standard Sirens, and on August 17, 2017, we were able to detect first binary neutron star merger. And we were also able to detect the electromagnetic counterpart to it. And this motivated the first standard Siren measurement of a real event. And we were able to get an H0 measurement of around 70 with its error bars. But since this is just a single detection that we have so far, future detections are expected to provide us tighter constraints and hopefully solve the Hubble tension that we have within cosmology. So about this project, the primary focus here is that how good of a Hubble constraint or we can obtain using LSST in future. We want to quantify how that the measured standard Sirens can affect the cosmology that we want to do with Hubble constant. The motivation here is that how much LSST will contribute to H0 precision, how many standard Sirens or how well standard Sirens could be detected by LSST. What are the factors that would affect the constraining power of LSST? There are selection effects and systematic effects that can come up. That's what we want to study within our project. And why do we want to do this? We want to study the impact that this is going to have on the science that we do in future. And if we happen to have some good results, and maybe we can advocate for more telescope time for these type of follow-ups for the standard Siren objects. Now, regarding the constraining power of LSST for H0, previously we have some constraint on H0 from the supernovae and cosmological microwave background results up to 2%. Previously, when the first detection happened of the first BNS merger happened and we detected the Scalable, we had different people doing predictions on how good things are going to be in future, how well we are going to be able to measure events in future and the resulting H0 precision from it. It was predicted that with every year there would be improvement in the detectors that we have, more detectors would be added to the network, and the number of events detected would increase with that. But as we know, the things have not been so ideal ever since the first detection, and there are always some ups and downs happening, due to which there is a need to update these projections. And there are other things also that we might need to consider. So this type of results, which have been done by the authors before, assume a scaling of 1/√n, where n is the number of events or for which the EM counterpart is detected. With increase in number of events, we expect that the uncertainties would decrease and we will have better H0 constraint. We might need to update this scaling and figure out if this is close to how things are right now with our camera and the detectors, and also investigate the size and impact of the systematic uncertainties that can affect our analysis. So the expected systematic uncertainties, the biggest one to consider here is probably the Marquis bias, which leads to truncation of our data set. On the right, I have the supernovae data set in which we get some truncation because of lack of ability of our telescope to be able to detect certain magnitudes to certain distance. This, we expect that we would have similar type of effect with kilonovae, and we can have this in fact resulting from telescope as well as the gravitational wave detectors. Subsequently, we want to look at the how good is the depth of the sensitivity of the EM searches, how these two uncertainties between the telescope and the uncertainties that can come from the LVK detectors, they interplay with each other. There's another factor of viewing angle dependency. For supernovae, we have spherical symmetry, so it doesn't matter from which angle we are looking at it, but in case of the kilonovae, there is this dependency which will need to be taken into account as well. So the plans for this project, we first of all currently working on the simulated data set for kilonovae. We need a data set that can accurately, or at least as good as replicate the kind of kilonovae that would be detected from the LSST camera. For this, we are coordinating with Matt Weisner's group and his students, where we have light curves from the Key and Data Challenge. And we're currently working on obtaining the data set that we can then work on and do progress with the project. So once we have the data set, the next step would be to apply those selection effects. First of all, figure out what would be the size of those uncertainties, what can affect our data set, or the kilonovae's magnitude, whether it is distance, whether this luminosity distance, or the magnitude of the kilonovae that we are detecting with the camera. So the big part here would be to figure out how to apply those selection effects. Once we have that filtered sort of data set, we can perform a cosmological fitting on the data set and then obtain some constraints, and that would be, and after that we would try to publish results here. And on the right, I just have these are again supernova results, but we expect that for our project, we would have something, a plot for the distance modulus here versus redshift, but also something for luminosity distance versus redshift. And that is also something that we might need to consider as a part of selection effects. And that's all. Thank you for listening. Any questions, please?
Questions for Simran?
Nothing from Simran.
Okay, and nothing online. So I will once again encourage people, think about what you heard, post your exciting question for Simran on the Slack workspace, and let's thank Simran again for the very nice talk. So, just before concluding, very importantly, many people today in particular highlighted the importance of cadence for their science case. There are still some shakeups that are happening. Things are not yet defined. Please show up if you can tomorrow at 10:30 at the session for the SCOC, regarding the SCOC decisions. And then there is, I think, a second session on the survey strategy led by Liv, with the math. So about how you can actually simulate different strategies. And I think some of us—
Sorry, on how you measure the science throughput on existing simulations of the survey strategy. Typically, the community doesn't simulate the strategy,
Yep.
but writes code to measure whether that strategy gives good science to you.
Thanks for clarifying.
I didn't want people to start designing strategies.
It's been a long day for everyone. Thank you for specifying that. And thank you all for attending. And let's clap one more time for all the speakers.